Right, good morning, everybody. I'm just going to get things sorted. There we are. Okay, so welcome this morning
Sean,
to this.
sorry.
Sorry?
Sean, sorry, are you recording?
Yes, yeah, recording now.
Okay, sorry.
Brilliant. Yes, good morning, everybody, and welcome to this introduction to network analysis. So today is going to be a pretty light touch introduction to this concept of network analysis and how we can use it in health service research. And then there's the two advanced sessions, which will go much deeper into actually conducting a network analysis and how to make it really useful for health service research. But hopefully this will give you an idea of what it is and why it could potentially be useful for the work that you do. So what we're going to do, we're going to start off, you've got quite a relaxing day today. There's quite minimal tasks and coding. So we're going to start off and we're going to discuss network analysis and its uses, then get a bit deeper into what a network is and look at the different components of a network. Then we'll have a little break, and after that then we'll get into actually doing some hands-on stuff. And one of the biggest tasks when actually conducting a network analysis is transferring the data, transforming the data so that it is suitable to be represented as a network. And this is always quite a big task that needs to be undertaken, but it helps you to understand how the network is being constructed. And then we'll use our data that we transform and build a network graph using the Python package NetworkX. And that'll just be a very simple graph. And then in the advanced sessions, we'll go on to looking at all kinds of funky things like animated graphs and how to customize the full look of a graph and different Python packages and some standalone ones for doing that. So kind of the learning objectives for today is, well, to be able to understand what a network graph is and how it's constructed, and really kind of understanding how that construction of the network is actually useful for health service research. And then to be able to transform the raw data so that you'd be able to conduct a network analysis on a data set. And that'll be transforming raw patient data, level data, for a network analysis, as this is kind of the level that is useful to be working at with your data. And then we're going to look at how to create a simple network graph in Python. So quite a nice relaxed day, hopefully nothing too stressful. Saving that for this afternoon. So network analysis and its uses. So network graphs were developed by Euler back in the 1930s. This is on my advanced set of slides, so I'm trying to remember. But basically, Euler was using network graphs to look at logistical problems. And since Euler's original work, they've been used most profusely to study the function of large and complex systems. We'll have a look at a couple of examples. And it's looking at the relationships and interactions between different elements of a system and trying to understand that in a way that is kind of that's graspable for humans, that trying to understand large and complex interactions is not something that we're particularly good at. As humans, we prefer very simple, obvious patterns. And when you've got very, very large systems, as healthcare systems tend to be, with lots of different components, lots of different departments, lots of different teams within that, all working and operating slightly differently, it can be very difficult to develop a picture of what all those interactions and relationships look like. And in order to be able to kind of grasp this, we need a way to abstract the system itself. Drawing a literal representation, anything that's too literal would be, again, too complex and difficult to understand. But if we can represent them in an abstract way, in a mathematical way, then we've got something which is much simpler and more understandable to humans. So the kind of things that network analysis is used for currently, just kind of some classic uses of it. Looking at things like airline networks. So you'd have airports within that and their routes that they're flying. And you'd look at the links between the airports and where they're flying to and from. Banking, looking at account holders and where they're undertaking their transactions. In social networks, this is kind of one of the largest uses of network analysis. And this is used by Twitter and Facebook and Instagram and everybody. All those recommendations that you get for people that, friends that you might want to link with, people you might want to follow. That's all the result of network analysis. And what they're using is looking at who you're closely associated with, but not associated with yet. It's that kind of, remember the big thing around 6 degrees of separation, that we're only ever separated from any other person by 6 jumps through a network that we can be related to or associated to many, many, many millions, billions of people through only 6 jumps. And that this is what social networks use, and they use the how closely associated you are, and some other stuff around it as well. Physician networks, so looking at doctors and patients. This is quite useful actually for looking at GPs and GP usage is one level that you can look at that. The data that we'll be looking at is people and patients and the services that they're using. So very similar to this kind of physician network idea. And then it's used an awful lot in logistical planning, particularly around supply chains. So looking at the movement of goods around by some form of transport. In this instance, they've given the example of trucks. And so being able to plan routes and to be able to plan how much of a particular goods are being moved between different warehouses, different storage locations, and then end point of sale locations. And this is one of the classic techniques that is used for all this kind of planning, whether that be, as the examples give, airlines, road networks, supply chains. It's one of those that sits behind and has been used for a long time in a very simple way, or simple-ish ways, to look at these kind of very large logistical systems. So an example of here of a network graph of the flight routes in the United States. These are domestic flight routes, and you've got your airports are marked as what are the nodes, and we'll come a bit more to this terminology in a minute. But our red dots are our large airports here, and the blue dots are our smaller airports. And then the green lines in between are all the routes that they're flying between the different airports. And so you'll hear today the terminology of nodes are the red dots, and the blue dots here are our nodes. And then the green lines are our edges that are connecting between the airports. They're the routes. So the connections are the edges, and the points that you're going between are the nodes. And yeah, this shows you've got here hundreds of airports, and thousands of routes that are being flown because of the different combinations between. It'd be very difficult to represent this as a list. It would take you an awfully long time to read the list of all the airports and all the different routes that they're flying. So being able to see these kinds of visualizations really help to rationalize what is a very large data set. This is an example of, this is a Twitter data set showing the links between different Twitter users. And you see George Galloway in the middle here for some reason, wondering what was happening at the time. It might have been that he was on I'm a Celebrity, Get Me Out of Here, I think he was on, and it was probably trending at the time. And so what they, Twitter use network analysis profusely to be able to look at who's getting the most tweets and retweets and likes, so that they can determine who's trending. Because that's not just done on numbers, it's also done on the proliferation of connections with other users. And so these are the kinds of graphs that they're using to see what's trending. These large dots will be the things that are large nodes would be the things that are trending. And you start to see all the different connections between them. This graph has another kind of dimension to it, which is the coloring of the nodes and edges. And these are representing different clusters, different groups that are more closely linked. And so this is one of the kind of techniques that we can use to start kind of rationalizing a graph to be able to see what's grouped together and how they group together, and start to see these kind of populations and subpopulations that form these small clusters that are linked together and working very closely together in some kind of way. So when we're talking about network-based operational modeling for healthcare, so this is where we're trying to use network analysis and graphs to try and represent the operations of the healthcare system. And what we've got in this graph here, we're trying to look at the graph itself as the service structure. So this whole thing will be the structure of how the different services, different teams are working together and how patients are moving between them. So the nodes themselves, these yellow dots, are the services that are being provided and the different teams that are providing those services. And the edges are their movement between the different services. And we can see that in this instance, they've got arrows on the end, meaning that there's a direction of movement between. So people moving from the Exeter AMP team down to the liaison and diversion team, and moving in this direction from the AMP team to the liaison and diversion team. And then they're moving off to other different areas, whether the CRHT or the forensics. And we can start to be able to develop a story around the movement of patients. And you start to see it take on a logical quality that in this instance, for those of you with we've worked in mental health services, will recognize that the allied mental health partners, they often deal with assessing people who might require being sectioned, and they will often refer on to the liaison and diversion team. And you will have a minority of people who require going on to the forensics team because they are of a higher level risk, and those of a lower level risk might be referred on to the crisis resolution home treatment team. So we can start to see the logic and movement between services for patients and the different requirements that they might have. And we can embed different information about how the services are operating within the graph itself. So we can look at the edge weight, and you'll notice that the arrows themselves, the edges, are of different thicknesses. And this is representing the weight, and this is the number of patients that are moving through the system, moving in a particular direction. So there's a large number moving from Delderfield to the Exeter Allied Mental Health Partners team. And this appears to be quite a key triangle between the AMP team, the liaison diversion team, and the CRHT. And so we can represent the number of kind of the usage, the activity that's occurring between two teams. And within the nodes themselves, you'll notice that the nodes are of different sizes, and also of different colors. And this is because we can embed information in the node attributes themselves. And these can be, whether it's the number of people that are passing through, the rate, we can attribute it to the length of stay. We can use a graph measure of something like centrality, so the connectedness of one service to the other services and how central it is within the graph. And we can start to embed lots of different information within these nodes, which makes them very useful for being able to track and understand the operations, because we can put operational measures within the nodes themselves. And when we get on to the animated types of graphs and looking at the actual performing analyses on them, you'll see that we can use this, bring in this information to inform the analysis itself, and use the analysis to inform the visualization. So what we're trying to do is building a picture of what is happening within the service structure, and it's built out of the services themselves and the links that the patients form by their movements between different services. And then we can embed information about their movements and about the operation of the services themselves. So the components of a network. So to kind of break this down a little bit further, the graph itself, it's a network graph is a graph-based representation of a system. And what that means is that it can be represented in Euclidean space or in a Cartesian coordinate system, and that we can basically plot it on a pair of axes and describe where everything sits. Sorry, please do excuse me 1 minute. There's a cheeky little robin in the house. I'll just be back. I've got the door open and just blown in. Where was I? So what we're doing is we can represent the nodes and edges on axes and say what their relationship, we can mathematically describe their relationship with each other. And it's this pairwise relationship between entities that we're trying to describe. So I'll just pick that statement apart a little bit. So when we're talking about pairwise, we're talking about relationships between two nodes. So two of our services, and then we're talking, because everything's about these pairwise, as an edge goes from one node to another. So it's a pairwise relationship, and the entities themselves are the services. And because we can encode both, we can encode quantitative properties of the system within the network structure. As I was just saying before, we can encode things like the length of stay, the waiting lists, the centrality of a node within the network. Its number of nearest neighbors, its number of connections with the rest of the network. We can encode the weights, the activity along the edges, but we can also say, put things like delay in transfer in an edge, and say how long it takes for somebody to move from one service to another. We're going to start embedding all sorts of information. The graph itself is just a tool to help us work with the data. So when we look at network graphs in their most simple form, there's a few different kind of attributes that kind of the nodes and the edges themselves hold. So the nodes are our dots here, and they're also called vertices. So if you see that terminology when you're reading around or in any of the literature, or I might accidentally slip and call them a vertex or a node. I try to stick to one and just call them nodes. Nodes seem to be a much more intuitive name for them, but mathematically they're known as vertices. And these are the dots. And then the edge is the link between one node and another. And this is where we get this pairwise relationship, that in this instance, V1 is related to V2 by a particular edge. And so there are lots of different types of graphs that we can have. And again, we'll talk about this much more in the advanced session. But at its most simple level, when it doesn't matter about order, so the link is between V1 and V2, but it can also be described as link between V2 and V1. It doesn't matter about order. That's just a simple, that's a graph. When order does matter, we have a digraph. So it's a directed graph. And that means that when we describe an edge, as in the earlier example, where we had arrows which were indicating a direction, that the order V1, V2 to describe the edge matters. Then the description V2 to V1 would be different to V1 to V2. And so that helps. That's particularly useful for health service research because people tend to move. We need to know what direction they're moving in. If we're just interested in looking at the links between services, then we might use an unordered graph, but we'd probably use a directed graph when we're interested in looking at how patients are moving between different services. And then we get our edge weight, which we discussed, and our different node attributes that can be embedded within the nodes. There are a few different little bits of terminology. We get things that are called parallel edges, and this is depicted between V5 and V4 here, that we can see that there is a link from V4 to V5 and from V5 to V4. These are parallel edges because they're describing movement between the two nodes in the opposite directions, but between the same two nodes. Then we get loops or self-loops, and this is seen at V5 here. So people they might enter a particular service and complete their treatment, but then need to come back in. So they're then back into the same service again. So they come back around. And these self-loops are an important concept in graph theory because we need to be able to describe that movement back around into the same node. Then we get adjacent edges, and adjacent edges are basically edges that are next to each other. So the edges that are described between V1 and V2 and V2 and V5 are adjacent. They stem from a common node and are essentially next to each other. And adjacent nodes are, we can see that V2 and V5 are linked by an edge, and therefore that makes them next to each other. So they're adjacent nodes. The interesting thing with network analysis and graph theory is that the terminology is actually relatively simple. Because it's a heavily maths-based approach, it has a lot of, they have to give everything a name, basically. So there's lots of this quite simple terminology just to grasp, to be able to understand some of the literature if you're reading around network analysis and graph theory. So when we actually come to build network graphs, the data that we require is relatively simple. We don't need enormous amounts, but it's very specific information that we need, and in a very specific format. So when you're building network graphs, you will, the robin's back, you will get the two different particular lists that will need to go in. One is your node list, and the other is your edge list. And node lists are commonly comprised of an ID. So you need a unique identifier for every node, and this is normally numerical. Then you will have a label, which will be your description in words. And then you can add as many attributes as you like. But the only two pieces of information that we must have are the ID and a label. And then the edge list itself. So this is what more actually describes the structure of the network itself. And there's two pieces of new terminology here. The first is source, and second, target. And what these are describing are the start and the end of an edge. So just to go back here. So if we're describing this edge between V1 and V2, and in an undirected graph, it doesn't matter which way around we describe it, but we need to describe it one way around. So V1 can be our source node, and V2 our target node. And so you're always describing source and targets when creating an edge list. And Robin's gone out. And we need that in an undirected graph. You will just simply have source and targets, and there will be a link between your nodes. When you're doing a directed graph, you need to describe each direction. So if there was links, for example, we'd describe V4 as a source and V5 as a target here, but then we'd also describe V5 as a source and V4 as a target. So you need both in your list in order to be in when you're creating a directed graph. For a self loop, the source and the target will be the same. They will both be V5. So in the edge list, this is what really creates our source and target. This is what creates our network structure. And then we can attach our attributes to the edges as well. So I'm seeing that I am actually running a bit ahead of time. So we're just going to hold on a bit, and if you don't mind, we'll just give it another 20 maybe 20 minutes. We'll just do a little bit more and then we'll have a little break. So what I'm going to talk about now is data transformation and how we transform patient level data into a suitable format for creating a network and to be able to describe our system structure and how it's operating. So the data transformation process, you want to be starting with raw data, patient level. And this data, as you'll see, in fact, actually, let me bring up a time. I'll bring up the example of the data that we're going to use for our first task. So when we look at this kind of, this is a patient level mental health data set that I've used, was used for a project, and I've developed an anonymized set for training. And what we've got here is a client ID, so a unique identifier for each patient, the date that they're referred to a service, and the date that they're discharged from a service. This, we got the referral source in this instance, although we don't necessarily have to use that. We got the team that they're actually accessing, and then some other information about the patient. So, and the services that they're accessing. So, general specialty, the condition that they have, the cluster, the care cluster that they're in, and some information about the services. So the setting, it's community or inpatient services, and the geographic locality as well. So we can use what is actually here a relatively simple data set in order to be able to create a picture of how the services are operating. So when we're doing the data transformation, what we're aiming to do is we've got to first of all clean up our data, make sure that we get everything's consistent, we get rid of negative dates and any particularly erroneous white space in categories that can make it that you end up with multiple instances of a team, and that's definitely what you don't want. So we've got to make sure we thoroughly clean our data. But the important thing that we've got to do is it's getting the order of the data correct in order to be able to develop our network graph. So what we're doing is we're going to order our data by patient first of all, and then by the order in which they have been referred to services, so that we can see the order in which they're using services one after, well, either at the same time or one after another, but then accessing one service first, then they're accessing another, and then another, and then another. So by ordering our data, we can infer that order that they're accessing services, even though they might be accessing multiple services at the same time. So once we've ordered our data, we can then create something called an adjacency matrix. And we'll discuss a little bit more about this shortly, but this is the kind of the core of any description of a network can be described using an adjacency matrix. And yeah, I'll discuss that more in a minute. It's easier to show you with an example. And we'll be using, so we're using unique instances of services as our nodes. And here, this is a kind of where a bit of the the art in developing the model comes in, where it all depends on the resolution of your data. So whether you have specific teams or a specific service or geographic localities, depending on what the resolution is of your data, at what level you want to be looking at it and how you want to subset or amalgamate different aspects of your data to create higher or lower level nodes. So at the lowest level, you'd have an individual team or maybe an individual person. At the highest level, you'd probably have something like geography or the trust itself. So depending on the scope of your data and the level that you're wanting to look at it, you need to start subsetting and amalgamating different elements of it. And what we do is we then iterate over the interaction matrix, our adjacency matrix, to create our edge list and to look at what our source and target nodes are and the weight of the edge between those source and target nodes. So these are just, in terms of data cleaning, just some things which you want to consider. It becomes very obvious very quickly when you start having multiple nodes which say the same thing in your graph. And this is normally due to things like erroneous white space, spelling mistakes, capitalization inconsistencies within the data. It's really important that that you do a really good job cleaning the data, first of all. So an adjacency matrix. So what we have here is a two-dimensional array, and our rows represent our source node. So each one of these will represent an individual service team, and the columns represent the target. And again, 0 and 0 here, or 1 and 1 on the rows and columns, will represent the same service. And our adjacency, so when we're building the adjacency matrix, we're basically going through our data and looking at the first service used by a patient, and then what the next service is that they used. And so the first service becomes our source, and our second service that they're using becomes the target. And we can go through the data in this way, going down service by service, then going from the second and seeing what the third one is. And then we mark this down in our adjacency matrix and count up the number of movements that patients are making between different source and target services. And so you can see here that some are marked with 1, others have higher numbers. We got 9, there's a movement of 9 between service 5 and service 5. So those self loops, so people coming back in to the same service over and over again. Between 5 and 6, movement to 2. And so we start, this is kind of the data underpinning the shape of the network graph itself. And from the adjacency matrix, then we then build up our node list. So we give each node an ID, and then we give it a label so that we know what it actually is, and then we can add different attributes to it, so things like mean length of stay, the median length of stay, and the setting. So we can have continuous and discrete attributes. Categories work as well as continuous numerical attributes. Then in our edge list, we are we know that we need our source and our target nodes, and these use the numbers, the ID of the nodes themselves. So that's how you link the node to the node list to the edge list, is via the ID. So it's absolutely essential that each node has a unique ID, because that's what your source and target are describing. And then we have an ID for each edge, unique ID, and the weight of each edge. I've also got type in here, so whether it's a directed or undirected edge. And this is something that is required by a program called Gephi, which we will have a look at, which is a standalone graph visualization software, piece of graph visualization software, which is very powerful. One of the best ones for creating very nice graph visualizations, but it's a bit fiddly to work with. But we will look at it because it creates very nice graph visualizations. And again, we can have both continuous and discrete attributes for our edges. So we've got weight here. We could have something like the rate of movement between nodes embedded in here as well. So all kinds of, things like the wait time, the delay of transfer between one service and the next, all sorts of different, anything you can think of, you can start embedding within the graph. If it's operationally describes what's happening in the services, you can embed it in the graph and start asking questions about it. So I'm going to stop here for a minute, and when we come back, we're going to look at an example of how we transfer the data set, which I briefly showed you earlier. And we're going to look at how we transform that data set in Python into the adjacency matrix, the node list, and the edge list. And then we're going to use that to create a network graph afterwards. So I think it's worth having an opportunity to make a cup of tea, and we will come back at, if we have, might as well have 20 minutes, as we're doing very well. I've kept today quite light. So if we come back at 20 to 11, so 11 at 10:40, come back at 10:40, just stay logged in, just stay on mute and with the cameras off, and yeah, save having to log back out and come back in. And we'll carry on in 20 minutes.
Sean, is it worth just seeing if anybody's got any sort of questions, just as we seem to be good for time?
Oh, yes, that's a very good point. Thanks, Dan.
So it's Heather here. I had an idea a little while ago, and I wasn't quite sure how to enact it. I belong to AFA, and one of the things I wanted to do was almost track who AFA members are interacting with, and see who are the real influencers, around the country.
Yeah.
So it was almost like I was going to send out a survey and saying, name the top 3 people that you go to if you've got a question, type thing, and so like build it back in. Is that the kind of thing that you're doing in a network analysis?
Absolutely. You're looking at the relationship between individuals and their influence. So, and you'd use some kind of proxy measure for influence. So you might look at it in terms of the number of messages that they've sent, or well, you can do it it depends on what data you can get, but yeah, you'd use some kind of measure of influence, even if that is simply the number of people that they're connecting with. So that will be and we'll look at this in the advanced sessions when we're looking at graph metrics. But so you can have you'll have multiple edges connecting with a single node, and that's called the degree. And if they've got a high out degree, so they're connecting with other people, then you might infer that they're heavily influential. And yeah, the graph will quite easily show that if you're looking at, collecting your data from those people that they're communicating with. Does that help?
It does. I just hadn't. I knew that I thought we wanted to do it for AFA, but I wasn't quite sure how to approach it. But this might start us thinking about ways and means, really. Yeah,
this is the perfect way to look at that kind of influencing behaviors. So yeah, that's commonly used in social network analysis, which is a slightly different area to what we're talking about here with operational, but social networks all uses the same mathematics and the same principles. It's just that you're using person data about person-to-person data rather than person-to-service data that we're using here.
And the only problem is getting hold of the data without having to generate it through surveys.
Yes, yeah. One thing that I don't, with NHSR, I was just thinking, there's the NHSR Slack channel. So I don't know if AFA has a Slack channel or something like that, but you can use whoever's the most, extract the data from that and use whoever's the most communicating and sending the most messages to people. And you can look at the message communication between different individuals if you can get the analytics out back, get the data out on that.
So you're mentioning Slack, so then presumably you can get yourselves can get data out of Slack for the
do you know what?
channel?
I haven't tried. I'd have thought that actually maybe with a paid for account you probably can.
Yeah, just to reassure you, I'm not harvesting all your data.
No,
I'm going to give you a bad rep, Dan.
I didn't think of it, but
I wasn't thinking about that. I was just thinking that if you knew that you could get data out, and you could probably tell us how to do it.
No, I'm not sure.
I don't know of a way. Sean might be right that it might be that it's paid for feature in terms of the analytics behind that. I haven't been. In fact, I think it is, because I'm pretty sure that when I set up the new HSMA channel, they put me on the premium thing as a trial, which I just largely ignored. But I'm pretty sure that one of the things was about analytics. So I think if you pay, and Slack is expensive if you're paying for it, very expensive. So I think if you pay for it, then yes, you can get that data, I believe.
But to be honest, most social network analysis is actually based on survey data a lot of the time. Anyway, it's only with web-based or things that they actually are able to collect data. It's Twitter, Facebook, etc. But if you're not operating on that level, it's normally survey data that you'd use.
Thank you.
Can I ask a question, please?
Oh, sorry, Adam, I can't hear you.
Oh, I think the mic's not very good. Can you hear me now?
Yeah, just about.
The data cleansing bit of the procedure, is there any easy way to do that, or is it just simply going through all that data, making sure there are no extra spaces and extra capitals?
So I'll show you some examples of that. And when we do the data transformation task after the break, we will see. I will show you some easy ways to do things.
Right, thank you.
Checking dates, but some of it is manual. But as you get used to what the issues in your data are, you can write functions to automate the cleaning process.
There are lots, just to chip in as well, there are lots of built-in functions into Python libraries that you can use, which I'm sure Sean will show you some of these, to clean up text data, for example. So in the natural language processing module, when we come onto that, cleaning your data is also really important for that. And that could be things like, removing capital letters and getting rid of identifying words that are supposed to be the same, but they've just been spelt differently or something like that. And there's lots of methods that are actually built in to allow you to do that. So yeah, don't worry, there's lots of things that allow you to automate this process so that the amount of stuff you have to do manually is minimized.
Okay, thank you very much.
Super. Anything else at the moment?
They've probably all gone on a break.
Okay, right. Well, yeah, let's come back at 22. We've still got 15 minutes. That should be plenty of time to make a cup of tea and have a bit of a break, and we'll get on with our data transformation task. Thank you very much, everybody.
Thanks, Sean. You can, by the way, you can you're probably aware you can pause the recording.
Right, so let's start recording and start sharing my screen. Okay. So, hope everybody had a nice break, and we're going to get on with our data transformation task. So this is really to help familiarize you with what the data looks like, because network graphs, to look at them, yeah, that's fine. But actually what we're trying to learn here is how to create them. And it's all about the underlying data structure, because that's what we actually perform analyses on and work with. The visualizations are just the pretty bit. So what we're going to be working with is, so on Slack and on GitHub, I've sent through in the materials, there's the data transformation.py file. So I'd like you to open that up in Spider. And this code is an example of how to transform patient episode data ready for network analysis and visualization. So this example is quite a good, I'd like to say it's quite a good one, because it works with all of the different, it produces a data set that works with the different Python libraries for network analysis, and also with Gephi. So the output files can be read in into multiple different packages. So when you open up Spider and open up the data transformation.py file, don't forget to set your working directory, because it's going to be trying to locate the data file that we're going to be using, which you've got to make sure is in the folder data. That's the PD data HSMA 2020.csv. And yeah, that should be in the data file, folder should be in the same location as the data transformation.py file. So set your working directory to wherever you've got the data transformation.py file. And what I'd like you to do, this is not a tough task, but it's an exploratory task to get you looking and investigating the data. So what I'm going to do is I'm going to split you into breakout rooms. Hopefully this will work. And I'd just like you to just sit down and just discuss and run the code line by line and determine what's happening within the code. Use print commands and or the variable explorer to look and examine the data transformations that are happening. I'm just going to bring over the data transformation.py file. So it's using pandas and NumPy only here. So we haven't got any extra packages coming in. And you're going to be, so this is the read-in, data read-in line. And so this is why you need to make sure that the data is in the right place. And yeah, it's just a case of going through. I put some comments in so that you can see the different stages, but it's actually looking at the data transformations themselves, and particularly around the adjacency matrix, how that's being created, and the edge list and the node list. The files themselves, there's outputs. So the adjacency matrix will be output as a CSV, which you can look at separately, along with the edge list and the node list. So what I'm going to do is just pop you into, I'm going to assign automatically. We're going to mix this up a little bit just for fun. So you'll be put into random breakout rooms with 5 participants per room, and just have a go, and just go through. And if you have any issues, I'll try and drop into each of the rooms. But let us know in Slack if you're having any issues.
Sean, I was just wondering what appropriate punishment is for you going over the 80 character limit vertical line. I think we should have you shot.
Yes, yeah. Well, that's I'll whip myself later. That's yes.
Fair enough.
Okay. So we just have kind of 15 minutes looking at this, 15-20 minutes, just to go through, have a good discussion about it. Okay, if you haven't managed to join a breakout room yet, there should be a button for you to click to join, and that will take you into your breakout room. Hi there, Vic. Just say I'm going to assign you to a breakout room. I'm sure we catch up on the task. It's we're just going through the data transformation.py file and exploring the data transformations that are needed for a network. So you should have an invitation to join a breakout room now.
Yeah, thanks.
Okay, so yeah, hopefully that was at least a useful exercise to remind yourselves this week of a bit of Python and to see data wrangling in action. Now we're going to look at how we can use this data to build a network graph. So this we're going to do as a bit of a code along task. So I haven't given you any code for this. It does rely on you having run the, I'm pretty sure I didn't put, yeah, it relies on you actually having run that first task to be able to create the data. And what we're going to do, the process that we go through when building a network graph using NetworkX is that we read in our data. So in this instance, it will be our node list and our edge list. We then create a graph object. So this is the NetworkX graph object, NX graph, that is responsible for handling our network. And then we've got to format our node and edge data into the correct final format for it to be read into the graph object. So this is where we create tuples of list and dictionary objects. And then we add the nodes and edges to the graph. And then after that, we plot the graph itself and draw it. So don't worry, I'm not going to ask you just to go away and try and do this. We're going to go through this step by step. So open a new script in Spider, and you're going to type the code in and run it as we go. You will need to move your node list and edge list CSVs that you created in the last task into the data file that we've been using in your working directory. So if everybody can do that first of all. If you haven't run that data transformation code, please run it now and to create the CSVs. And
Sean,
let me know if anybody has any issues.
Sorry, Sean, I think it already has done that because mine is already stored in the data subfolder.
Ah, is it in there already? Did I?
Yeah.
Did I have it put out?
I think
you wrote them out, Sean. You explicitly wrote them out to a data subfolder path.
Did I? Excellent. Yeah. Excellent. I'm ahead of myself there. Then that's I thought ahead and did that. Excellent. So they should be in the right place if you've run that code. Okay. So new script, and we're going to start by importing NetworkX as NX. Remembering our kind of conventions for shortening these words, these package names. NX is what's used for NetworkX. So we're going to start the first two lines, import NetworkX as NX, then import pandas as PD. Then we're going to read to the nodes, to a nodes variable. We're going to assign our node list data frame. And to edges variable, assign our edge list data frame. If I go too quickly, shout at me. Just shout. Oh, can you go back? Otherwise, I will just give a pause and then move on. So then our next line is that we're going to assign to the variable G our graph object. So this is basically initializing an empty graph. And that's just G equals nx.graph with a capital G.
Is that convention, Sean, for the to have a capitalized variable name for your graph?
Yeah, they tend to do that for the graph objects. That's
okay.
what, well, in terms of convention, it's what they use in the documentation.
Yeah.
So just kind of sticking to that. But yeah, you can call it my graph, anything like that.
Yeah,
but,
yeah. No, just interesting because obviously it's I've seen a few other things. There's some things in NLP where it's convention to do have a variable name that's capitalized, which obviously you wouldn't normally do.
Right. Okay. Yeah, I think they tend to do it when you've got very specific custom objects. At least that's what I've seen with the network analysis packages.
Right. Yeah.
Okay, so we've got our graph. Now, what we need to do is to create the node inputs, and these are tuples. And if you remember from Dan's introduction to Python, tuples are immutable objects. That means once they're created, they can't be changed. And it just means that they're held stable. They're very stable objects for us to work with. And the way that NetworkX likes to take lists of nodes is as tuples. And so we create a tuple of the node ID and a dictionary of attributes. So for every node has a dictionary attached to it. So what we're going to do in our first line is we're creating an ID list, which are our node IDs. And so from nodes, we take the column ID and we convert it to a list. That's our first line here. Then what we need to do is, so our attributes in this instance are just going to be our labels. So what we're going to do is we're going to create a new data frame simply with the column label. So our node labels. So labels equals pd.dataframe, open brackets nodes, square brackets to say this is the column that we want to extract, and we're extracting the column label. And that's given in single or double quotes, it doesn't matter. And then what we're going to do is we're going to convert the label to dictionaries. And we're going to create a separate dictionary for every label. So we're creating our variable label dics. So that's it's a dictionary of dictionaries. And so we're using from labels, we're using the function toDict, and the orientation is by records. So this means that it's creating a separate dictionary for every record. And then finally, we can create the tuple. So this is, I've just called it variable node tuples. And here we're using list comprehension. So this is where we can do a for loop in a single line. And we're creating a tuple of R. So this is basically for R, which is the length of our list. So our list, our ID list, and our dictionary of dictionaries are both of the same length. So it's using the length to know how many times to go through. And what it's doing, we use the zip command here to zip.
I'm sorry, are we supposed to be typing this out while you do it or just watching?
Typing it out while, yeah, you're supposed to start a new script and to be type
Well,
along.
I am, but I'm obviously not typing as quickly as everybody else. So the
Where
one
are you
just,
up to?
well, is the page just before this, the g.nx.graph?
Yes.
Yes, okay. So if I've got that, could you mind just going over what the other bits mean? Because I've sort of lost what they mean as I've been typing after this page, the next page. This one.
Okay,
Thanks.
so I'll just finish my explanation and I'll go back over it.
Okay.
Yeah. So what we're doing when we're creating the tuple is we're looping through our ID list and our labeled dictionaries, and we're zipping them together into a tuple. So we're taking the ID element from the list and the dictionary, and we're putting them together into a tuple and outputting that. So just to go back over that, we are creating a list using the toList function of the IDs in the nodes data frame. We're then extracting from the nodes label column, creating a new data frame simply with just the labels column, and that's called labels. We're then converting the labels data frame and converting each row to a dictionary object, and so that we have a dictionary of dictionaries. And this is called label dicts, which we've got to be careful how I say that. And this is where we're just converting each individual one to a dictionary. If we were using more attributes, we'd have more than just the label in each dictionary for each node. But in this instance, we've just got the one attribute, which is the label. And then we're creating a tuple, which is an immutable object. And that means that once it's created, can't be changed. So it's a nice stable object for us to use. And that we're creating node tuples by zipping together the ID of the node and the dictionary of its attributes. And we're doing that for all of each node in turn. And we're using list comprehension here, which is this in square brackets, to run a for loop in a single line. These using list comprehension and zip is something which is extremely useful in Python, and makes your code very concise. And I think there'll be more examples of this as we go through the course.
Yeah, there's some in the natural language processing, Sean. It's very similar to the way you have to do it on this. Yeah, no, it's a really good technique to be able to learn. Okay.
So how would you add another attribute in on the labels dicts then?
So what we do with that is where we're just taking the column label into our labels variable here in the data frame, we'd have other rows, other columns that we might have length of stay or length of stay, waiting time for the nodes, and we'd have additional columns, and then we'd go through exactly the same process. It's just our data frame would be larger.
Okay, so it would just be comma, nodes, and then again, and a different thing, length of stay. So you'd put the nodes again and keep repeating that piece there inside those brackets.
Yes, but you'd
Yes.
have to put that in square brackets, I believe,
Okay.
in order to be able to, because you create a list
Okay.
of the columns
Okay.
as your input argument.
Okay.
Okay. Right. So now we've got our node objects. What we now need to create are our edge objects. So the edge inputs are tuples again. And here we're creating, we need the source ID, the target ID. So remember, these are a start and end points of our edges, which are given by our node IDs. And again, a dictionary of attributes. So our edge tuples are source, target, and then dictionary of attributes in that order. So we're using exactly the same process again. Our source list is going to be getting the source column from the edges data frame and converting it to a list. Our target list is taking the target column from the edges data frame and converting it to a list as well. We then get the weights, and because those are our attribute that we want to attach to our edge, and we create a new data frame just with the edges weight column. And then we convert the weights to a dictionary of dictionaries using the dict function and orientating by records. Again, then we're converting to a tuple. So our edge tuples, we're using the same list comprehension, tuple R for R in, which is our loop syntax, saying do this for all the records. And we're zipping together source list, which is our list of source nodes, our target list, which is our list of target nodes, and the weight dictionary, the dictionary that contains the weights for each edge. So one of the things that really confused me with tuples is I always thought they had to be made of a certain number of objects, or they could only take 2, 3, 4 things. Tuples can take as many different arguments as you want to put into them, but it's simply that immutability of them. I just find it a funny name. It's one that it took me a while to get my head around.
Good way to think about them, Sean. Actually, I found is to imagine them sort of, whatever your arrays are, or your lists of things, that they're kind of frozen. Then you're freezing them in time. So like I say, it's that immutability, isn't it, that makes them unique.
Yeah. Great explanation there, Dan. That's really helpful. Yeah, and it's funny because you think, oh, okay, is that a special thing? And it is. Yeah, it is a special thing to freeze something like that. But yes, just a very strange name. I'm sure there's a reason. There's always a reason for these names. And I'll probably get told off for calling them tuples. They're also called tuples. It depends who you're speaking to.
I like it when Tom says tuple with his northern accent.
Tuple. Okay, and moving on. So now we've done the hard bit. We've created all of our node tuples and our edge tuples. So now what we're going to do is we're going to add them to our graph object that we created earlier. So we do that simply with the syntax G, which is our graph object, then using the dot operator and the function add nodes from. And we add our node tuples object to that. And the same for the edges. Our graph object G dot add edges from, and the edge tuples object gets added there. So this is a way you can add, if you look at the NetworkX documentation, there's a few different ways that you can add nodes and edges to a graph. You can add them individually, or you can add them from an adjacency matrix. But this, I find, a little bit more of a generalized approach. All the different packages take their nodes and edges from node and edge lists, and you can work with the format of the node and edge lists with all the different Python packages for undertaking network analysis. So it's just a little bit more of a generic way in. So now that we've added our nodes and edges to our graph, but we haven't told it how we want it to visualize the graph. And one thing is, one of the hardest things about graph visualization is working out how to place all of these many nodes and edges in relation to one another. And this is very much something of an art. And in the advanced sessions, you'll see, we'll talk a lot more in depth about graph layouts and just how difficult it is, especially with large numbers of nodes and edges. But with NetworkX, we need to determine a position, a set of coordinates for our nodes, and determine, and this essentially gives us edge, start, and endpoints. NetworkX and the other network analysis packages in Python come with a set of algorithms for determining what the coordinates of the nodes should be or could be, just basically giving suggestions. And some of these algorithms are better than others, depending on the number of connections that you have between the nodes and the number of nodes and edges that you have within a graph. In this instance, we're going to have a play with the Kamada-Kawai layout. So what we're going to do is assign to the variable pos nx.Kamada-Kawai layout, and the input argument to that function is our graph object. So what it will do is it will go through and assign each node a position on a Cartesian coordinate system, so on a XY graph, and assign where each node should go. And that's what it's saving into the pos variable. And finally, we can draw that. We've now got everything that we need. We've got our graph object, which has our nodes and edges in it, and we've determined our position for our nodes, and hence our edge, start, and endpoints. So we're going to create our plot by using the function nx.draw. And the arguments that we pass into that are our graph object, first of all, G. Then we need to define the position. So the argument pos, we assign the variable that we created, pos. And then just a little bit of aesthetics, we are going to change the node size to 100. Say with labels is true, and change the font size of those labels to 10. And when you run all of that, you should, hopefully, fingers crossed, get a network graph. So I am going to bring my copy across. And here's one I prepared earlier. So let me just make sure that I've got my working directory set. That's always a good idea. So when we run this, import networkx and pandas. Ooh, no, I haven't put them in there. Everyone else got their data, but I put it in the wrong place. So we can read in our edge list and our node list. Create graph object, G, and then to create the node tuples, you can see create our ID list, which is just a list of integers. We then get our labels, which is just a data frame of our labels. Then we create the label dictionaries, which is a dictionary, it's a list of dictionaries. So each one of these is a separate individual dictionary using the key, label, and the value of the label itself. We then get our node tuples, which are our ID here, and then the dictionary as well. And then we do the same for our edge tuples. And in this instance, we can see we get our source and our target IDs, and then the dictionary for the weight. Then we add our nodes and edges to our graph object, create the position, which is a NumPy array of coordinates for each node within a Cartesian coordinate system. And then we create the plot, and that should render in your plots window. There we are. And that is your first network graph. Does anybody have any questions on any of that at all?
So if we'd added in another attribute of length of stay, the median, would we be able to make the size of them larger based on that attribute?
Yes, yeah, absolutely.
Yes. Okay.
Yeah, and we'll see examples of that in the advanced session. I'll go through all of that in much more detail. and how
Okay.
to create very, very nice looking. That will be in the second session, in fact.
Okay.
Let me just go back to the presentation.
Yes.
So in the optional sessions, we'll
Yeah.
be looking at different graph types. We'll be looking at graph metrics, so how we can describe the structure of the graph and how we interpret graph metrics in relation to health service operation. We'll be looking at how graph visualizations work, because the graph algorithms for determining the layouts and how you can do custom layouts are quite complex. And then we'll also be looking at interactive graphs with Plotly and HoloViews.
So the distance between the different nodes on the plot we've just produced, what is that then? The distance between the different nodes.
So in the positioning, algorithm that we used, I am not sure. Sometimes things like centrality is used to determine how things are clustered, how different nodes are clustered together.
Because some of them are nearly touching, aren't they?
Yes.
And others are very far apart.
Yeah, it all depends.
I mean, touching, but they've got no route between them.
Yeah, I'm just, this is all what we cover in the later sessions. I am just trying to think. I can't remember, because this, I can't remember what the Kamada Kawai layout is using to determine its distances. But yeah, those distances and the positions will be determined by different features of the graph itself.
Okay.
So Sean, is it all down to the layout then, in terms of how, like the one that you showed us earlier with the Twitter and how it is all color coded and things like that? Is that all dependent on the layout that you choose?
Absolutely, yeah. Yeah, so what they're likely doing there is, and again, we'll see, what you do is calculate whether it's clustering or the modularity of the nodes, how they link with other nodes. And then you assign clusters to them, and you can use that to inform the layout, so it groups clusters of nodes together more closely.
Cool.
Could I ask about, so the example here with mental health services, what sort of question was that trying to answer, and how did that work? Just to understand how it could be transferred to other
Right, okay, so yeah, so the ways that I've been using network analysis with mental health data has been to, one, map the interactions between different services. Is incredibly useful on its own to know which services are interacting with which other services, how patients, the direction that patients are moving between services. You can start to look at which are the most highly connected services, those that are facilitating the transfers of care for patients, where you're seeing people coming back into services, where you've got lots of cyclical behavior is one thing that we look for. So that trying to determine if people are not receiving the most appropriate service because they're simply coming back in and using the same service at a high rate of repetition, and that's an issue because it indicates that there's not an appropriate service for somebody. and looking at the length of stay and the accrual of waiting lists across a system, and where there might be knock-on effects, that people might spend a short amount of time with one service, then they're referred on to another service which doesn't have sufficient capacity to take the patients that are being referred on to them, potentially because their treatment time is much longer, or they just have a huge backlog with insufficient capacity. And starting to be able to identify these kinds of operational issues within the data, if that makes sense.
Yes, thank you.
I'm also exploring at the moment and trying to see if I can get a master's project together around it on looking at the application of machine learning for networks and trying to predict future system state, which is slightly involved. But there are specific graph-based graph neural networks which use graph data, because the data is more complex than the kind of data that you traditionally get, even for image analysis. But graph approaches can be very useful for image analysis, as well as understanding different, the kind of more complex and deeper patterns that occur over time within networks, large systems themselves, which we can't analyze using classical methods. Okay, so just to say, I will put up the code that for that graph creation. I'll put my copy of the code up there on Git for you, and there is within that as well, just to show you quickly, actually.
Sorry, is it all right if I ask just one thing? So it's the weight, the edges weight. So in the first script, it's the weight in the edges data frame, which is causing that difference in the plot. So in the edges data frame, how is the weight calculated in there? I don't quite understand that.
How is it calculated?
In the edges data frame, in the first script that we did, the data transformation script. In
so
that one.
That's to do with the number of patients. So it's the count that you get when creating the adjacency matrix.
The more
Because
people there are going through.
That's it. Yes. Yeah. The number of people that are moving from a source service, a source node, to a target node.
Okay.
Because if you remember, we're going through the data, looking at each client and their movement, and counting and adding 1 to each source target relation that each time, and that count becomes our weight.
Okay.
Yeah,
that's great. Okay, thank you.
Just to say, so in the copy of the code, the graph creation code that I'll put up on Git, there are other layouts in there as well that you can test and try. So for example here, I'll just run the graph using the Spring layout. So you can see that these are different layout algorithms, which are based on random seeds, and so they do change each time. We will look much more in depth at this in the advanced sessions, because it is an incredibly deep and difficult topic. Creating decent graph layouts is not an easy thing at all, and a lot of them require you get to the point where you have to create custom layouts for every data set that you have, which are not the simplest thing. See an example of spectral layout. There's a very old layout there. And the other one is to have a look at some of the, if you are interested in network analysis, is to have a look at some of the NetworkX documentation. So there are a whole range of tutorials on here. The documentation is really quite good for NetworkX. Talks all about adding attributes, directed graphs, multi-graphs. It all gets quite in depth. There are galleries to show you different examples of different types of graph that you can get. There are some, let's just see if there's good examples here. Yeah, there's the code for lots of different examples, all the reference material, the different algorithms that you get. We'll go much more into this next time, actually looking at all the a large variety of the different graph metrics that we can use to understand system function and structure, and really putting that into context for you. So I say please do join if you'd like, and yeah, I hope to see you for the advanced sessions. If anybody's got any more questions, I'm happy to hang around for a bit. I know we're a little bit early finishing, so bit of an extended lunch break.
Would it be too much of a big ask just to show us Gephi in the next 5 minutes? Have you got something set up already?
I have nothing set up, I'm afraid, Richard.
I retract my question.
Yeah, I will be demonstrating Gephi in the next sessions, and again, they'll all be recorded. So if even if you don't attend those sessions, you'll be able to look at the recordings on the YouTube channel. Ellen, have you got your hand up there?
Yes, yes. I always have problems to find the link.
Sorry, Ellen, you're going to have to speak up. I can't hear you.
Okay, can you hear me now?
No, I'm sorry, Ellen. I can't hear you at all. You have to turn your microphone up.
Is it fine now? Yeah?
Okay, I can just about hear you. Yep.
Okay, sorry. I always have problem to find the afternoon link for the afternoon class.
Sorry, say that again.
The link for the afternoon class.
Oh, the link for the afternoon session. Right, yes, so that is in the calendar invite that you'll have received, the Outlook calendar invite, and that's the second link in there. That's for Dan's session this afternoon, and Dan, I think we'll also post it in Slack.
Sorry, Sean, I missed the question.
Thank you a lot.
Was that regarding this afternoon?
It was the link, yeah, the Zoom link for this afternoon.
Yeah, I'll post that in a second onto Slack. It'll be my normal the normal link for my sessions, but I'll repost that on Slack. I'm just saying, so we'll start at 1:30 as normal, so you'll have a bit of an extended lunch.